name's Ayush, and this is my Lab 5, which is Choose Your Own Adventure. For this lab, I chose the slinky example. So here our goal is to determine the effect of gravity and drag force on a slinky that's falling by comparing the predicted and observed motion of it. So the predicted was computed through the glow script code, and we created models with and without drag force, and then the observed we used tracker and monitored the position. So some physics principles to remember. Newton's second law, we've been over this in a few previous labs. Force is equal to the change in momentum per change in time, F equals ma. Newton's third law, for every action there's an equal and opposite reaction, which is kind of apparent because it's a slinky, kind of force goes both ways. And the velocity and position update to calculate changes in position, and a new one, drag force. So here are the formulas. Most of these we have seen before, except really drag force. Force equals negative b velocity squared v hat, where b is the density of the air. And this was a screenshot that I took from the tracker model that I made. You can see that the position of the slinky was tracked over several intervals, and you can see this, I guess, more apparently in the graph as it began to fall. And I guess we can see the data a bit more clearly from the computational model. So this was some of the initial data that we had: the initial position, the velocity, the mass, the time intervals here. The mass is 0.175 kilograms, some of the formulas that we discussed earlier. And yeah, this is kind of what we used to compute the position data. And then with drag, it's pretty much the same, but we did plug in the b variable that I discussed before in the formula for drag, negative b v squared v hat. So this was the constant for b on Earth. And here are the results that we got between the tracker, the gravity model, and the model with drag force. As you can see here, the gravity model does drop in position faster. So this shows us that drag is definitely a force that is significant in our example, and a force that acts upward, and a force that allows the position to fall at a slower rate than if it did not exist. And some discussion questions. Why does the bottom slinky remain motionless? So yeah, the slinky is basically a huge spring. So the bottom slinky is affected by the opposite forces of tension / spring force up, and then gravity down. So when the slinky is released from rest, it begins to fall from the top, but because it's a spring, the bottom hasn't caught up yet, and this is because the downward force from gravity is opposed by spring force in that instance. So after a short interval, the energy travels down to the bottom of the slinky, and then the entire slinky begins to fall as a unit. In conclusion, the experiment allowed us to see how gravity can affect objects in different ways, and when gravity is not the only force in the system, it's important to focus on the other forces that could potentially have a change in behavior. So this allows us to predict motion in a more efficient and accurate way with more complicated systems where there's more variables in play. And that's all. Thanks for watching.